today, which covers how to model and assess cooling towers, chillers, and central plants in EnergyPro. This training today and all of the other trainings are being sponsored by PG&E and being delivered by Partner Energy, and this is in support of the Multifamily Upgrade Program. Today we're going to be hearing from Kyle Brumfrit, who's the Sustainability Consultant at Partner Energy, and he'll be going over all of the details and nitty-gritty nuances of cooling towers, chillers, and central plants. This training is the culmination of our Tech Topic training series, which started in April and is completing today with cooling towers, chillers, and central plants. If you missed any of the previous Tech Topic trainings, all of the recordings are hosted on our YouTube page. Easiest way to get there is just to search in your favorite search engine for Multifamily Upgrade Program YouTube. Alternatively, you can get there from our website, which is multifamilyupgrade.com. We are also hosting a separate series of webinars on Building Performance Institute Building Analyst. This is a new way of delivering the BPI training in 1.5 hour to 2 hour webinar chunks. And that training series has also begun. It began in early May, and we're continuing on. The next session is planned for after the July 4th holiday. If you would like to attend any of those trainings, please get in touch with us at the Multifamily Upgrade Program, or you can go to our website to find registration links. Again, like the Tech Topic training series, all of these past trainings are available for free on our YouTube page, so check those out. If during the course of today's presentation you have any questions, please feel free to chat or raise your hand or try and get a hold of us in any way possible using the GoToWebinar feature on the right-hand side of your screen, and we will answer your questions. We'll hold the questions and answer them in chunks at the end of each logical break. The end of the BPI training series will offer you a chance to get some hands-on diagnostic testing training. If you would like to attend this training, there's going to be a full-day opportunity to get hands-on experience on August 20th, and there's an opportunity also to challenge for the written portion of the BPI Building Analyst exam on the 21st. Both of those opportunities are being hosted at the Stockton Energy Center. If you're interested in a BPI field exam, you're going to need to get in touch with Partner Energy to complete that. Any and all of these opportunities are open to you as partners of the Multifamily Upgrade Program, so thank you for joining us today, and go ahead and take it away, Kyle.
All right. Welcome, everybody. Thanks for joining us in the previous sessions, if you have been, and welcome if this is your first time. So today we're doing the cooling towers, chillers, and central plants discussion. We're going to get into kind of what the basic understandings are of a cooling tower, chiller, central plant, kind of how to model it in EnergyPro, and some kind of helpful tips. So I just want to start with a little basic understanding of what a cooling tower, chiller plant system looks like and how it works. I guess I should just start out by saying don't be afraid of the size of the systems. They are large, but they basically do this exactly the same thing as what our normal, split systems may do, or any kind of refrigerant cycle is trying to do. It's just trying to remove heat from a space. So, this is basically an oversized system that you would see in commercial use mostly. However, you may find them in multifamily projects as you go out and start putting through the program. So we wanted to bring this to light in these sessions. So with that, I'm going to try to show you. I got a little laser pointer here. So the three major components you have for the cooling cycle, you would have your chiller. You got your cooling tower, which is your condenser side. It's rejecting the heat. And then you have your indoor air handler. It could be a 4-pipe fan coil, VRV, variable air volume, sorry, VAV, variable air volume, or constant air volume, or just a packaged air handler unit. Many different options in that sense. I worked on projects in the past with central plants, mostly in a campus setting, so dormitory setting where it's like a 4-pipe fan coil inside, and it was using a central plant to provide the cooling and heating for those systems. So much broader, much larger scale, but it can be used in multifamily just in the same sense. So so we have the chiller here, basically using just cooling the water down very cold, so it's going to be supplied to your indoor air handler, where then it's taking the return air or any outside air you may have. It's going to be is everybody can hear me okay? I just got a notification about the sound mic. Is everybody can still hear me?
I can hear you loud and clear.
Okay, great. So we have the cold water coming off of the evaporator side. That's going to be going to your indoor air handler. You have return air and outside air that's being mixed in a mixing box or return plenum kind of thing you may see in a multifamily scenario. Running over the cooling coils, cooling that air down and pulling the hot air out. This is then warmed up and taking it back through the cycle where it goes to the condensing loop. It takes that hot water now out to your cooling tower and is cooled down and back through. So I'll get more involved in it, but this is a simple, basic understanding. I'm trying to show you the comparison between this and what you may be used to seeing with your split DX kind of systems. So here's your plant within EnergyPro. What you see here that's circled is your chiller. So this is your chiller information, your cooling tower information, and we'll be talking about the pumps. Not going to be really getting involved in the thermal storage or anything like that, but we'll stick to those 3 items. So, so here in the chiller section, you're going to have some options of what types of chillers you'll be looking at. So just like any other kind of system input or assembly input that you would have in EnergyPro, you click on that guy, and it will take you to another screen. So on the screen on the left is basically a screenshot of EnergyPro, and then the image on the right is just a chiller, just a basic chiller that we have in here. And there's the 3 components to it. So you have your evaporator. The evaporator is going into your indoor unit. And then you have the condenser side, which is taking it to the cooling tower, typically located outside or on a roof, and then you have your compressor. So what we see here, I wanted to show you kind of, there's, again, just like you have AHRI or ARI ratings for equipment, you'd go to the AHRI website. Well, big, large units like this, you have ARI ratings, and so you want to make sure that you're getting information that is used and is rated at these conditions. So typical operating conditions are your leaving chilled water temperature is at 44 degrees. Chilled water flow rate is typically 2.4 gallons per minute per ton. Entering condensing water temperature is 88, so that's the temperature of the water going out to the cooling tower. And then your condenser water flow rate is typically 3 gallons per minute per ton. So inside these barrels is what they call these barrels of the chiller. There's a bunch of different tubes, and they're very small. Could be hundreds of them, depending on the size of your system. But that's where the water is flowing through, and it's getting either cooled down or being taken to your condenser to the outside unit. So the evaporator is going to have a bunch of pipes inside there that's going to be able to running the water along it, and then it's going to be leaving to go to your indoor unit. Efficiencies for chillers are typically given in kilowatts per ton. So you're inputting that information in here for your electrical efficiency, kilowatt per ton. You have your capacity. Again, these are very large systems, so they can handle a lot of indoor units, and you're obviously, to size your chiller or your central plant, you need to know what your total load is and what your tonnage is to offset and to satisfy the load. So so there's a couple different types of chillers. Two major types of chillers. You'd have a vapor compression chiller and an absorption chiller. So the vapor compression chiller is most common type. Is when you have refrigerant or water undergoes phase change, is your vapor compression chiller. So we're used to refrigerant going through a phase change to remove heat from a space, and same is for the chiller, and we use water. Chillers and central plants have been around for a very, very long time. Water is a great, so in the beginning, of the days of air conditioning, water was the way that we used the means of changing, taking heat out of a space. So, you might see pictures of old cities, back in the day where you had a bunch of cooling towers outside. You might even go to some cities now and see that there's still some cooling towers sitting up on roofs. And they were used before we got into, getting into refrigerants and figuring how that would work. Absorption chillers have been around for a while too. Mostly absorption chiller was kind of used, or absorption, the means of keeping things cool is used actually in RVs. So I believe it was like in the early 1920s. They were using the absorption kind of pneumonia water combination for keeping refrigerated items cool in RVs, which I thought was pretty interesting. But basically, it's using a heat source, solar energy, fossil fuel flames, gas turbines, or water heaters, and then that would provide you the energy you would need to drive the cooling process. So it's a very efficient way to do that, and sometimes you get into calling them cogens or trigen situations where you would have byproducts of that one system. So you're able to have a gas turbine, which is going to provide electricity, hot water, and air conditioning. Then it's what you call like a cogen or a trigen, depending on how many different things that one item is producing. The options you have in EnergyPro for your types of chillers, you have the reciprocating chiller, the screw chiller, and the scroll chiller. So, and this word always gets me. Centrifugal is not the way you should say it, but that's the type of chiller that I'm using right now, and it uses rotating impeller blades to compress the air. So if you can cut a hole or cut down the middle, you'd see two rotating impeller blades that's driving that compression. The reciprocating is using pistons for the compression, and then your screw is using counter rotating screws to drive the compression, and your scroll is using interlocking spirals to scroll and to perform the compression. So it's just different ways of compressing that vapor. And then you have the absorption chiller options, which is 1- and 2-stage absorption. uses low pressure steam or hot water to drive the absorption cycle. You have a gas absorption, uses gas cycle from a liquid to a vapor. And you have a gas engine driven, which is very similar to what you see in an automobile, to use as a gas fired engine to drive the compression that you needed for your chiller. And then heat recovery, and we all you should be familiar with what heat recovery systems are, in a residential standpoint, where you're basically taking that heat out that you're exhausting out, and it's mixing with that colder air, trying to basically preheat that air using what is being exhausted to help reduce energy use on that side of things. So those are the options you have in EnergyPro to select what type of chiller you're working with. I'm going to talk about the pumps. So when you're excuse me, when you're dealing with the chiller pumps in EnergyPro, you do have an option under the chiller section here to put a pump in. However, you don't get the flow control option. So variable speed drives, which should be like the #1 energy saver option that you provide a client, when you go out there and you see that it's just like it's a constant volume control, constantly running, or if it maybe be just like a 2-stage, low and high. Variable speed drives are great energy savers, and you want to be able to capture that energy in EnergyPro. So what you do is you actually use the secondary pump inputs, put in your flow rate per pump, your pump multiplier, all those good things, your design horsepower, and if you can remember from the previous slides or the previous webinars we had, design power is your brake horsepower. So you want to make sure you're getting your operating conditions for your motors and pumps to make sure you're not overestimating that energy use. The flow control, it has just those options that I was saying before: continuous, 2-stage, and variable speed. So typically, if you go out, like I said again, if you go out and you see that there's a old inefficient pump that they have on there, first option would be to replace that pump, and you will be able to prove to them the savings that you may get by replacing them by using this secondary pump section of EnergyPro to calculate those savings. So we're going to get into the cooling towers now, and so this symbol over here is supposed to represent a cooling tower. It doesn't look like a cooling tower, so I just more looks like some kind of, I don't know, water heater or something. I don't know. No, it doesn't look like a cooling tower, but here's where basically we're using this as the condensing side of the equipment. And these, like I said before, typically located outside on a slab or up on your roof. This is the equipment that provides the heat rejection. So we're going to get into that here now. Image on the right. This is what's called a cooling tower cell. So you see in the industry, that's what they call these. They call them cells. You can have multiple cells depending on the load you need. And then there's a couple of different ways of these cells being configured. So it's a pretty simple concept. You have that hot water that that comes through the top inlet, right? And it's being dispersed over what's called the fill. So there's a bunch of different kind of fins, and they just basically try to spread that water out so it removes the heat more effectively. And then there's a big impeller fan at the top that is helping drive that outside air that's colder than your hot water through the fill. and it removes the heat from the water. So if you ever go out in the morning and it might be cool out in the morning and you see big plumes of steam coming out, the roof of somebody's building, you don't have to call the fire department. It's not on fire. It's basically just steam, doing its job, and the cooling tower is, working. It's going to cool down that water. The water is just going to dribble down or rain down on the fill and then get collected in this sump. Now, obviously, through evaporation, the water, you're getting less water coming down here, so there's going to be a fill. There's going to be a fill that's in the bottom, and I believe if you can see it in this picture, it's this guy right here, and I'm kind of squeezing it, or I'm circling over. That's going to be the fill that's going to replenish the amount of water that you need, because you're losing water through evaporation. So then you now have cold water that's down here, and it then gets piped back to the chiller to start the whole process again. Another thing to know is that, obviously you get, water to refill that. It's going to have impurities and, particles and things like that comes in the water. So there's basically a bleed valve on those on the bottom, and that they will bleed off some of that water to make sure you get that, so the system doesn't kind of get all dirty and crummy and whatnot. So from the fill water that comes in, or the street water, or whatever you want to call it. So I'll show you that flow diagram again. Now that I've kind of gone through it, it might help out, make sense. So again, the evaporator, this is the side that's going into your space, and that temperature of the water, I guess, it really depends on the specs of your chiller that you're using and where you're installing them, or they're being installed. Runs through your coils. It's warmer water then coming back that goes to the condenser side, and then that hot water goes over to the cooling tower to remove the heat, basically taking that heat out to the outdoors, much like you see a condensing unit out in your house. It's the same deal. And then it goes back through and does the whole cycle again. So that's in a nutshell. That is what the cooling side of a central plant is doing. They're very efficient systems, but mostly used for larger scale operations. You can have full districts, full communities built on this. I know when I was a kid, my dad told me that their whole neighborhood used, a central plant in this sense. So, they built the whole entire neighborhood with this, and it's happening more and more, district, cooling kind of systems. So here's EnergyPro. Here's the cooling tower types. You can have an open circuit. So basically an open circuit is what I was explaining to you there before, where it's just, the water, it's just, free water that's coming out, is being exposed to the elements. So that's called an open circuit. Now you can have a closed circuit, which is basically that water is now going through pipes, and it's basically not going to ever, be met by the outside elements. It's still using the outside air to cool down on the cooling tower side. However, it's just not, water that's raining down on the fill. It's a different scenario the way that it goes. So that's a closed circuit type of cooling tower. And then you have different kind of capacity controls. So like I said, you have the variable speed, modulates the airflow, so the tower capacity matches the load at the set point. So that's your fan, that large fan, the impeller fan. 2-speed fans causes the fan to cycle between off, low, and high. And you can have your 1-speed fan to maintain the tower set points. So you have a 1-speed fan that's maintaining that tower set point for temperature. Cooling towers also can provide fluid bypass valves on them. So this is really important if you're in cold climate. Much like it's much like your condensing unit, your AC unit, you wouldn't want to run your air conditioning when it's cold outside because you're kind of fighting the whole premise of taking up the heat of the space. Bad things can happen to your condensing unit when you're trying to run your condensing unit in cold weather. So what happens in the fluid bypass is that instead of the hot water going at the top here, it basically bypasses another valve and bypasses that whole process. It gets dumped into the sump, where the water is sitting there, and then it gets sucked back out this side. So it's not cooling the water down too much, because if it gets too cold, then bad things can happen on the condensing side of the equipment. So fluid bypass valves can be put on cooling towers to make sure that your system is going to function and operate for the long term. So in EnergyPro, you select the type, open or closed, your type of capacity control for the fan, your output, and then your approach temperature, set point temperature, and a minimum water temperature. So basically, approach temperature is the delta between what is coming in and out. So I might have an approach temperature of 10 degrees, 15 degrees. Probably wouldn't have much more than that on the design side of things. Set point temperatures, basically your set point temperatures of the fluid water coming in. And then you have your minimum water temperature going out, so 65 degrees, and then it gets cooled down even more through the evaporator side, and gets down to maybe 55 degrees, so it goes through your fan coil or 4-pipe fan coil or air handler at that temperature. So that's what approach temperature, set point temperatures, and minimum water temperature is. Engineers, depending on where you're at and what climate you're at, you may have different approach temperatures, set point temperatures, and minimum water temperatures. You also may have different performances that go on along with your cooling tower based on those temperatures. So very important to capture that information or gather that information from the engineers' record that are working on the projects to make sure you're operating you're inputting the appropriate information. So on the heating side of things, so central boilers, central hot water boilers. So on the left, I've shown you a picture basically of industrial sized boilers. And you're going to be, in EnergyPro, you're going to be putting that under the heating hot water side. So I always think of it, your wet HVAC on the heating hot water side, and then your domestic hot water, we all know, is for domestic use. Now, it's going to have the same situation where you have pumps and you have, head to overcome, and you can make sure the water gets to where it needs to get to, and your set point loop temperatures, things like that. But just keep in mind, this is when you're actually going to be using the heating hot water tab. I would imagine in most scenarios, we're all using the domestic hot water tab when we're doing EnergyPro modeling. But when we're dealing with central plants, you're going to be using the heating hot water tab. So hot water used to heat your space as opposed to hot water used for domestic use of showering, washing hands, and things of that nature. Similar in all your other EnergyPro files, you click on the new boiler, or if it's going to be an existing boiler, in our case, maybe replacement, that kind of thing. You have your whole library, system library in there. You're able to select the system you want, modify the system you need to accurately reflect the system you got in the field. So you'll be doing all that from there, gathering all your information like normal, using nameplates, photos, going to the correct websites or resources to get performance values to plug in there. And then you have your pumps. To pump that water through the building, you're going to have, it depends on how big your building and how long your pipe lengths are, but you're going to have a certain flow rate per pump. Your design horsepower, again, is your brake horsepower, and then the flow control of that pump. So there's only one input really on one section in the heating side, which is here, as opposed to when you're dealing with central plants, you have kind of two sides, you have the chiller and you have the cooling tower. And when you're dealing with the hot water side or the heating hot water side, you're just dealing with this tab. Pretty straightforward. The different types of indoor units that you typically use here, you could have your air handler if it's a single zone or multi-zone. Like I said before, variable air volume. And then constant air volumes, and also chill beams. I've modeled chill beams before using this approach. You would use the 4-pipe induction in your drop-down for indoor units. But again, here's a little diagram that's showing your air handler unit in there in the middle. So you have the very cold water and then the cooler water. So it's slightly warmer. It's trying to reject that heat through the cooling tower, and then it just kind of runs through the whole cycle again. As I said before, these systems, they are very large. You might go and be kind of nervous about verifying them or checking them out or being able to model them, but try to keep it simple in your head. The same principles as the other systems, just in a much larger scale. So get yourself familiar with the way the systems operate and function. There's a lot more piping involved. So you kind of want to know how to track that stuff down when you're out in the field. If you do ever come in line with a central plant. To recap some helpful tips. So chillers come with chiller curves. So you can get chiller curves to satisfy part loads. So some very similar to your variable refrigerant flow VRF systems, where they modulate down based on the load. A chiller can do the same thing, and it uses what's called a chiller curve to satisfy those part load demands and needs. So chiller curves can be put into EnergyPro. There's another tab basically under the chiller section that it's called curves, and you're going to want to get that information from the manufacturer. Based on the system you have, you can give them the information you have for your set points, and they can provide you with a chiller curve to match that system. And then you may have, well, there's a lot more engineering that goes involved in that. We don't need to get into the details right now, but understand that the chillers they're not just full on, this is what you get. They can all be customized, and they can satisfy part load just as much as they can when they're fully operating and everybody's trying to run their air conditioner at the same time. So you'll be able to measure and quantify that savings and a part load savings for your building using the chiller curves. The pumps thing, I bring this up again because it was one that I wrecked my head for a while. I couldn't figure out how I can use the VFDs in the EnergyPro software, and then come to find out, you can use the secondary pump section to account for VFDs and plug that information in there. Again, if you go out and you see just a constant running pump, or two-stage pump or something that's just on and off and whatnot. VFDs, man, they save people a lot of money. Um, you know, even pool pumps. If you're dealing with savings for pool pumps, VFDs, changing those things out to get more efficient savings is always the option to go for, in my opinion. So. You can add up to 4 different chiller plants. I don't think anybody in this webinar is ever going to have to model more than 1 chiller plant, if any you see it out in the field. But just keep in mind you can have 4 different chiller plants, different sizes in there, and then you can have multipliers if you have more than that. You can use multipliers, but probably not going to really need to worry about that too much. So yeah, I think that takes us to the end. If we have any questions, go ahead and we can open that up. That's the central plant.
Great. I haven't seen any questions come in from the audience, but I've got a question for you, Kyle. Can you describe a little bit about, from your experience, the exchange of information that you would go through with the engineer to kind of define or refine your pitch or your modeling of what's existing in the field? How does that data exchange go, and is it just a one-way? Is it usually just one way? The engineer dictates how big and how the system is configured, or is there some nuance to how you model it, and as a result, how the engineer has to design and implement it?
Okay, yeah, I mean, good question. I try to use the modeling to help guide the team, so I try not to think of it as like a one-way or anybody dictating anything. Really, just kind of let the model speak for itself. Share that information with the engineer, and really just have that open conversation of what is the actual need and load that you have to deal with, and then a lot of times it's not only engineers but system reps. If you call up a McQuay or Carrier or something like that, those guys are pretty good with getting you the information you would need, like the chiller curves, or what is more efficient, a scroll type or a screw type, or what would fit this application the best. I think modeling it first always gives you a good playing field to work from, and then just share your findings. Make sure you're all using the same internal gains, the same assemblies, things like that. And then I look to the engineers definitely for their experience in the equipment, their overall general knowledge of how the functionality of it is going to happen. Controls, controls is a big thing. For these larger systems, you definitely are going to have a separate controls person, and most of the time engineers use those guys to really fine-tune the systems and the functionality of them. So when you're dealing with a system like this, there could be multiple players involved with how you get your recommendations out there.
Sure. Thanks. Yeah, definitely. Since we don't have any other audience questions, I've got another one for you. I've dealt with one chiller system, and it was in a building that was in Sacramento, and it was probably built in the early 1900s, potentially even before then. So my perception of chillers and central plants in multifamily is that the systems are largely phased out of the market and were used at a time and a place when, I guess in Sacramento, my thinking was maybe the water was so abundant that it seemed like the obvious choice to implement that strategy for trying to implement a cooling system. My question is more about where do you see these systems most often, and do you see any new systems being put into multifamily buildings, or are people sort of moving away from this in multifamily?
Well, the project that I worked on that used it, it was a dormitory. It was a new construction dormitory at Cal State University of Fullerton, and it was over 1,000 beds. So quite a large campus, 6 buildings, 5 stories each, and it was a central plant. They put in with 4-pipe fan coils in each of them, outside air ducted to the fan coil. But yeah, that was as recent as, I guess not so recent, but 2009. That went in, and I mean that was a system, and they are very efficient. I think when you're dealing with something like that, a campus style setting, I think it all depends on who's paying for it, right? So like in that sense it was campus dormitory, so they're not charging kids rent, right? Or they have their their fee to stay on campus, but it's not like it's not like a multifamily building where you're having utility charges and things like that. So I don't think, unless you're starting to put in meters for water use or things of that nature, metering the heck out of a multifamily building, you might be able to quantify the utility charges, but it's going to be hard to do that when you're dealing with a central plant. So in a multifamily world, I haven't seen it being used at all in the 9 years that I've been doing this. But for more campus style or district kind of communities, it's definitely used a lot. And I think like when you were in Sacramento, you saw it being used there. I mean, like I said before, water, before refrigerants were even thought of and used as a means to remove heat from a space, water was really the thing that people use. So I don't know, you see a lot of old movies or whatnot where there's just cooling towers, plumes of steam coming out, or just old vacant cooling towers sitting up on a roof that they eventually retrofitted and changed out, but they kept the cooling tower there. It's not. I don't see it very often in multifamily.
So we're not likely to see these systems in multifamily, but it's good exposure to know that the cooling tower, chiller, central plant configuration is an effective way to provide cooling for a large campus project, potentially multiple buildings with one plant.
Yeah,
and the
definitely.
only issue there is how do you allocate who pays for what?
Yeah, I mean,
which is why you don't see it in multifamily.
Yeah, exactly. I think there's a lot of like district-wide, energy efficient people out there doing these district-wide plants, and they're starting to figure that out and how they can quantify it. But I think it's still in its infancy, you know what I mean? It's still very young, hasn't been, tried, tested, and proven kind of thing. So I feel like a lot of things go around in cycles. So, we might have been using a lot in the early 1900s, and, we might find a way, in the 21st century to use it again. But until then, I think until we can find an effective way to do it, it's going to be one of those things that sits on the shelf for a little while.
Sure. But I do think there is some merit to understanding the differences between how we're moving energy around these buildings in comparison to a forced air system using variable refrigerant flow, or in this case, variable water flow. We're just swapping out water for refrigerant. So if you cross that threshold of a large enough project where variable refrigerant flow doesn't pencil out or doesn't make sense, chillers could start to see some use with the more onerous requirements that we're starting to implement in California, at least, and elsewhere in general, about forced air system duct requirements, location and sealing and everything. So just improving the efficiency of the systems. I could see a real use for chillers if the property or the campus was large enough.
Yeah, for sure, for sure.
Yeah, I think that jives with kind of everybody's expectation or experience is seeing these systems in existing multifamily, not so much in new construction. So there you all are. If you see this system, you now have an idea of who to go to for questions and also what to refer to for how to take a shot at modeling this system. Kyle, this was really interesting for me, so thanks for giving us this information today. And if any of you would like to follow up with myself or Kyle, you know how to reach us. Our contact information is on one of the first slides of this presentation, or you can reach out to us through our toll-free number or through our website, multifamilyupgrade.com, and I can put you in touch with Kyle or vice versa. So Kyle, I'll leave the last word to you, and thanks for the presentation.
No worries. Well, thank you, Mike. I appreciate it. It's been fun, guys. I enjoyed doing these for you guys, and you know, hopefully we can do it again in the future. Get another set of topics up, and just kind of help broaden the experience and the knowledge base. So thank you all.